Welcome back to the Energy Forum, a podcast from the Center for Energy Studies at Rice University's Baker Institute for Public Policy. I'm Ken Medlock, Senior Director of the Center for Energy Studies. In this two-part episode, we're talking about one of the biggest environmental challenges we face today, plastic waste. Believe it or not, a vast majority of collected plastic waste ends up in landfills, but new recycling technologies could help change that. We'll explore what advanced recycling is, how it works, and what challenges it faces to achieving the scale required to make a difference. Leading the conversation is Rachel Meidl, Fellow in Energy and Sustainability and Deputy Director at CES. She's joined by Dr. Marco Castaldi, Professor of Chemical Engineering at the City College of New York. Rachel, take it away.
You've named a number of different advanced recycling. It has many different names. It's referred to generally as chemical or molecular recycling. And so even for those of us that are considered experts in this field, we're oftentimes perplexed by its taxonomy. So, I mean, what are the broad categories of advanced recycling? I mean, what is it accurate to say they fall into like dissolution, depolymerization, and conversion? And then under that broad spectrum, there's all different types of technology platforms under each one of those?
Yeah, so and let me comment on just something that you said about the evolution, the complexity, in the years of technology advancement. I compare it to the automobile. The core of the automobile, not electric vehicles, but the core of a gasoline or diesel automobile is the combustion within the cylinder that then turns a crank and drives the wheels. That hasn't changed in centuries. What has changed? I mean, you remember some time ago that you can have your car running in your garage, and if you close the garage door, you would get poisoned by carbon monoxide, a product of a complete combustion. Okay, that then got, let's call it, changed because there was catalytic converters put on there. Then there was improvements in the fuels that were made. Then there was improvements in the precision of the machining of the automobile engine. Then computers were brought on. Then fuel injectors were brought on. Then it was determined, okay, well, some of these things don't have to be metal. They could be plastic. So it lightened it up. So exactly to your point, the core heart of it has not changed. But the different developments that has made it, now we went from, 5 and 8 miles per gallon to 30 and 50 miles per gallon with, 1/100th of the emissions that were there. So the same thing needs to take time and develop for these different types of technologies. But to the point of, what kind of categories do they fall into? I would say they mostly fall into, let's call it, in my mind, two main different categories, right? And sound pretty simple, but we could give a little detail: thermal and non-thermal. In thermal, especially for plastic recycling, it would break down into pyrolysis, where you just heat it and you cannot have any air or oxygen in there. And then you have gasification, where you actually you're heating it again, you have a little bit of air or some oxygen in there. And pyrolysis mostly makes liquids, and gasification, as it kind of sounds, it makes a gas that then you can process. It's called a synthesis gas. And then the non-thermal processes, again, fall into definitely mechanical recycling. That's non-thermal. But then in terms of the advanced recycling ones, if you will, it would be considered depolymerization, dissolution, where you're using a solvent like a methanol, like a glycol. Some even try to use what's called supercritical water, which is just water at high temperature and high pressure. And those solvents serve to break down the plastics into constituents or monomers, of what they're called, that are within the solution that then have to get separated later. So I'd say those are the kind of big categories that they fall into.
Okay, that's really helpful. And I think it's going to be helpful for the listeners to understand that advanced recycling is not a single process, and treating it as one overlooks both the risks and potential, because as we've already stated, it's a broad category that has distinct subcategories, each with very specific processes, unique outputs, very different feedstock requirements, right? Different operating parameters, and all very different impacts and performance characteristics, whether that's energy and emissions profiles, resource inputs, system economics. And so I see that as a real opportunity here of where we need independent verification, life cycle data, regulatory clarity, more important than ever. I mean, and this requires scientists and engineers to help validate, test, and qualify and measure these things. So I think there is a real risk in dismissing or categorizing all advanced recycling as unscalable or harmful. I mean, in my mind, being in the energy industry, I mean, it's like condemning the entire energy sector because of the environmental impacts of maybe one energy source. And just as we differentiate between fossil fuels, solar, wind, hydrogen, nuclear, whatever, each of those have very distinct impacts, scalability, and risks and roles. And plastic recycling technologies vary widely in maturity and environmental performance, economics, and purpose. And so I think a smarter approach when we talk about this is to assess them based on outcomes and safeguards and system integration and not so much on ideology. And so that brings me to something you've already stated and covered a bit, but I want to tease this out a little more, is that conversion technologies are the most studied chemical recycling technologies. So like pyrolysis, gasification, and they typically involve the thermal breakdown of the waste in an oxygen-starved combustion-free reactor, right? And so we oftentimes mistakenly see a mischaracterization of pyrolysis as incineration. But from a scientific and engineering perspective and regulatory perspective, they are very separate and unrelated. Can you help with this differentiation? What does the science say about this distinction?
Yeah, so that's very good background. Specific to that question, you know, I look at it as in the thermal processes, you've pyrolysis, you got the gasification, and then you have something, what really is what we do with waste, controlled combustion, waste to energy. But as you say, many people just term that as incineration. What's the big difference? The big difference are couple-fold. One is these conversion technologies for plastic serve to preserve the constituents, the monomer resins. So again, think of polypropylene. That's a very common plastic that we use in a bunch of different things. A thermal conversion like a pyrolysis system would just break down the polypropylene and warm it up and heat it up, so you'd have a liquid, if you will, shorter chain polypropylene. Propylene itself is a gas. If you continually heat it up, you'll have propylene gas. Okay, and then you can polymerize those. You can join those propylene molecules and entities into a polypropylene. But in a pyrolysis system, you want to heat it up enough to just, get it to flow and not really generate too much of a gas. The gasification systems would take that same polypropylene and maybe bring in just a little bit of air, and you termed it right. It's an oxygen-starved thermal reactor. And there, what it would start to do is make a synthesis gas, carbon monoxide and hydrogen gas. Carbon monoxide and hydrogen gas could be made into any type of final plastic product, as well as a number of other products, including a fuel. And so, right, you've got the pyrolysis system that's preserving that kind of molecule. So this way it could just be then, put into processes that manage the propylene. Gasification takes that same propylene or polypropylene, generates it into smaller molecules, the carbon monoxide and hydrogen, that then could be built up to make a whole bunch of other things. The combustion process, that would take that polypropylene and have so much air in there and so much oxygen that it would generate CO2 and water. And the primary product of that kind of combustion process is heat. And then, of course, CO2 and water. And so there's now no provision to try to use that carbon dioxide and water to remake any kind of material. What you've done in the combustion process is take that material and extract the energy from it. Whereas in the other two, you've taken that material and you're trying to just convert it into entities that allow you to make it back into a similar material.
So essentially, so it maintains that carbon. So pyrolysis maintains that carbon in the final product of that conversion reaction rather than releasing carbon as carbon dioxide, for instance. And so, I mean, that's a great distinction between the combustion and pyrolysis, which is oftentimes spoken about as one and the same, but totally distinct, and also very distinct in the waste hierarchy, that the pillar of waste management, right? That where you have the reduce, reuse, recycle, energy recovery, disposal, which includes landfilling and incineration. And it's like preferential order of treatment, where at the top of where you have reduction, reduce, that is like the most preferred, all the way down to the least preferred. And somewhere along there in the recycling portion of the hierarchy is where advanced recycling should sit. Advanced recycling, or the recycling or the energy recovery. So as we talked about, each one of these different technologies require different inputs, but they also have very distinct outputs. And so one of those outputs is that it has the potential to produce fuel. And I know that is a point of contention for a lot of people debating advanced recycling. And while plastic waste-based fuel would certainly reduce the consumption of fossil-based fuel, those fuels generally fall outside of the principles of a circular economy because it's a one-time energy consumption. But I know like that is a major bone of contention for a lot of people, is that, well, how circular is something if we're just going to be burning it for energy recovery? Do you have any thoughts on that?
Yeah, and this gets to a couple of things. So you're right. We should always follow reduce, reuse, recycle. And then, of course, now the work that we've done over the past 20 years is really try to refine what I would consider the waste hierarchy. And I'll give you a very specific example. In the past, the EPA just had reduce, reuse, recycle, and then disposal. And, that's not really the case, because after reduce, reuse, and recycle, well, there's anaerobic digestion, there's composting. This is kind of like a recycling process. And then, of course, as you get to, let's call it disposal, if you will, that's when you have things like, the combustion systems, the waste energy, where at least you're extracting the energy out of it. And then, really final disposal is landfill, but there's many different landfills, right? There's, landfills that almost don't recover anything, and it's almost literally a dump. But then there's very modern landfills that actually extract landfill gas that's generated and make energy. So in terms of that process, really where I think it comes to is the material that you cannot recycle, or the material that doesn't have a value, so it's quote unquote non-recyclable. Now, what can't be recycled? Okay, think about potato chip bags. They cannot be mechanically recycled. They could be thermally recycled, but there's actually a lot of issues with that thermal process because of all of the different materials that are in there. It causes some issues, which we can get into if we have time. So now the question becomes, is it better to just put it into a landfill, or because it had some inherent energy in it, to extract that energy and then, let's say, whatever, 1 barrel of crude that I'm not going to use, it's going to offset that because I'm using the plastic after its useful life. The details, really, the devil is in the details there. Really, how the accounting goes, what you're really offsetting, what is the electrical grid that you're offsetting, and so on. So from my perspective, it's definitely better, and this is also agreed upon now by the EPA and other international bodies that kind of have a refined hierarchy. It's better to extract the energy from it because that's going to offset virgin energy resource that you have to pull out of the ground. However, if you're comparing it against hydropower, then that's a different calculation.
Exactly. And I talk about this all the time in my research. Is sustainability is all about trade-offs, and we have to look at the trade-offs across the entire life cycle. And that includes understanding the economics up and down the entire life cycle, understanding the environmental performance and characteristics across the entire life cycle, and understanding some of the social constraints alongside that. And so it is a complicated process and it's complicated decision making. And there are many considerations. And having managed hazardous waste facilities and earlier in my career, and I can attest to the stringent environmental safety and performance standards that facilities are held to at the local, state, and federal levels. And a lot of them comes down to regional availability and capabilities of technologies. And so there's certainly many improvements and reforms that are needed in policies to keep pace with innovation, but it is not an easy decision where the hierarchy, the waste hierarchy is always the optimal decision always lies at the top of the hierarchy. There's so many other considerations when we start talking about sustainability and that intersection between the economics, the environmental, and the social aspects of it. And so let's talk about some of that. What are some of the environmental safety and performance standards that facilities operate under in the context of these processes and technologies? Like where do we need to see improvements?
Okay, so again, I want to preface this. I'm not a regulatory and expert and so on, but in terms of the work that we've done and we've helped and worked with and took measurements of facilities to kind of ensure that they would be under or meet the permitting standards. To me, really, so I think the environmental permits, number one, are generally okay there, but second, on the aspect with newer technologies that come up, I think that the regulatory environment needs some what I would consider quantitative and scientific flexibility, engineering flexibility, right? That's not to say, oh, you have a new technology, give it a try and let's see what comes out of it, and then we'll figure out a regulation. I'm not saying that at all. What I'm saying is that you've got facilities now that are, let's say, managing different streams, different things, and the regulatory environment normally is set up for, say, air permit. Okay, the air permit, when you do something like that, you say, okay, so what category is your facility in? Oh, we use coal and we're generating electrical power. Okay, so you're in the power sector. So here's the regulatory framework that works for you and what size and how many kilowatts you're making. All that's very, very well understood. However, when you come to facilities that say, well, we're going to melt down a plastic and you have to generate a gas when that happens. That's just unavoidable. Most of it, a large majority of it, in the 90%, 85%, is still a liquid, but there's gases generated. Okay, the question is what to do with that gas. Best thing to do is don't want to release it into the environment. It's not good enough to, and there's not enough of it to try to separate it, condense it, and sell it. So usually you burn it. Well, the pyrolysis system needs heat, so you burn that off gas for heat. So you're basically using some of the plastic that's coming in to make some heat. Okay, but now when you're burning it to make heat, okay, regulatory environment says, well, air permit, well, you're making heat, so you're a heat generation entity. Well, no. That's a very small amount that we're made. That's a byproduct of what we have, and we're just trying to valorize it and monetize it to use it, so we offset how much more natural gas we have to bring in. Well, the regulatory environment gets confused there, right? Because they say, well, you're not a waste processor. And they say, well, what are you talking about? Most of the material coming in here is waste. So that, I would say, improvement in the regulatory environment needs to kind of think outside the box. Right now, it tries to put these technologies in a box. Are you this type of technology, that? And the answer is, well, we're both. We're processing waste. So we're a waste handler, we're a waste processor. We're yielding an output that's going to make a product. So we're like a manufacturer. And yeah, we're kind of, burning our own, let's call it off gas to kind of save energy. So yes, we also generate some heat. So we're processing waste, making an output that goes to make a product, and we generate our own heat. Where in the regulatory framework that fits is very, very confusing.
It is, and I think this whole space needs almost like a regulatory gap analysis or a policy analysis to really understand what's the most holistic approach we can take. Because we want these facilities to be regulated, right? and they fall under the full suite of air, water, waste, and safety regulations. And I think that is what it's going to take for some of these to really scale and commercialize, is really understanding what are the state and federal regulations and that they're required to comply with, and the different industry standards that might be required with some of this. Because even though pyrolysis doesn't create any direct combustion related emissions, it still could generate some emissions, right? Whether they're VOCs or NOx, or depending on the feedstock composition and operational conditions, it could generate waste like particulate matter from incomplete conversion. Carbon dioxide and CO2, if produced gases, are combusted for energy recovery. And so all of these things need to be taken into consideration. Do you, from your point of view and working with these technologies and working with different folks, I mean, do you believe that some of these risks are being managed transparently and credibly? I mean, because you and I have spoken about this before at great length, like the need for mass balance or chain of custody type of accounting. I mean, I think those types of things are going to be necessary in order to really understand where the impacts are. Life cycle based tools and frameworks needed for accountability. I mean, what do you think?
So let me kind of frame it this way, that these facilities are stationary, so they must meet permits, and they will meet permits, because all a regulator has to do, all an inspector has to do, all somebody in the public has to do is say, I want measurements from that facility. The facility can't go anywhere. So it's ripe for, and it's a stationary facility. So they will meet their permits. Otherwise, they will not run. My estimation is that what would accelerate, what would really help these things come online faster, is if the regulatory industry, the regulatory agencies are more, let's call it, nimble, more adapting, more acceptable. Again, that is not to say cut corners. That is not to say, just try to move faster to just move faster. But there are, and I'm on a couple of them, there are engineering societies like the, American Institute of Chemical Engineers, the American Society of Mechanical Engineers, and others that have, very knowledgeable people that understand these things, that can work with the regulators to kind of get things to happen faster. Because let's face it, if you look at a study that was done 5 years ago about the types of technologies that were coming online, and you try to find those technologies, in operation, many of them go bankrupt or they close down because they can't get operational, because they're held up by permits and regulatory framework. And that's just costing money. I will say, in terms of, let's call it the mass balance, the chain of custody, that is more, in my mind, to demonstrate in a quantitative way that the amount of material you're bringing in, how much of that goes to product. And for the very first part, you want to just make sure that that number is high as possible. So if you're bringing in a certain amount of, plastic, and only 20% of it is going into product, that's really not a good system. Even if it's meeting regulatory environment, even if it's creating energy and so on, you should really be getting up there around 60, 70, 80% that's going into product. And that's where that mass balance comes in. I'll also say something very quickly about life cycle assessments. We have to be very, very critical of life cycle assessments. And you had mentioned something about the data that's needed, or gaps that are there. Because when we do analyses, we don't do life cycle assessments, but we do critical evaluations of LCAs. We make sure that these LCAs are using data from operational facilities. It doesn't have to be huge facilities, but it's got to be operational data, because otherwise the assumptions that are going into there about what kind of feedstock they're getting, about what kind of operating temperatures they're going to be, about what purity of product, if those are assumptions, you can make these studies look like these technologies are, the answer to everything. Or you could make these studies look like these technologies can't do anything. So to me, a critical piece of that chain of custody of doing the mass balances is also getting data from operations that then work into the life cycle assessment to say, what is the overall impact from this data of this operation?
Yeah, right. That is such a good point. It really hinges on the data quality and the source of that data. And that is very important for understanding and interpreting a life cycle assessment and looking at things across the life cycle. And we'll be having a future episode here on mass balance and life cycle assessments. And so that's something for our listeners to tune in for when we have that. And so I guess this all kind of points to how do we select and scale the right recycling technologies, considering the feedstock quality, the cost and economics, the regional infrastructure, the safety and performance, all of those things have to be really scrutinized. And thinking about how does policy and certification standards, how does that define success, especially around what counts as recycled, and going back to that whole mass balance. And at the end of the day, we really have to build end-to-end value chains beyond the reactor, right? Including logistics, purification, offtake integration, all of those things. And so as we look forward to the next decade, Marco, what do you see as the most urgent scientific questions or technical frontiers that we need to be thinking about, that we need to address to move plastic circularity from aspiration to reality? Where should the research and policy communities be focusing their energy to ensure that we're not just chasing scale, but we're really building credibility and resilience into the system?
Yeah, that's that's a hard question. That's an engineer trying to predict the future, and it's a non-Newtonian trajectory. My opinion is, I would say it's in three main areas. One is, I'll call it public responsibility. And if you think about plastics, right, they're made as consumer products, and the consumer demands certain performance, right? And so there's a large responsibility from you and I to make sure that we're, again, reducing, we're reusing, but also then we're working to put things in the right receptacles and so on. So that's one big one, because even in New York City, where there's a lot of awareness of it, there's very little practice of it. Second one is, I would say, is in the area, again, like I mentioned, the regulatory framework, the permitting areas, where there has to be a trust. There has to be bringing on the right entities with the right expertise to say, okay, this technology doesn't fit in box A, B, or C because it has components of A, B, or C. So what kind of regulation do we want to make and establish that allows this technology to operate in an environmentally benign or low impact way? So there has to be that, what I would consider, again, I call it flexibility, but at least the framework there to think out of the box. The last one I would say is, there has to be, again, I'll call it a continued push on fast sensors, fast logic, and things that can identify where in the stream contaminants are, what types of plastic you have, and then what kind of technologies can be used to try to get the right plastic resin into the right stream. That doesn't mean that it should be only one pure type of resin, but again, there's categories that the purer they are, the better these technologies will be able to operate continuously. Again, these facilities could operate. What causes, let's call it, disruptions is on the incoming feedstock. Again, if it's under operating conditions for polypropylene, and all of a sudden a whole bunch of polyethylene comes in, well, that first of all will change the product output stream, and then you have to change the conditions of the operating system to make sure that, things don't go awry. The faster that could be known that you have polyethylene coming in, and you can anticipate on exactly when it's coming in, and then the faster you can change operating conditions to accommodate that, that would just make things operate much more efficiently, and I would suspect much more economically.
Well, that's awesome. And let me try to summarize what you said. I mean, so I concur. We certainly need detailed information on volume chemistry, format of plastics, and technical experts and engineers like you to help identify, analyze, and optimize these solutions to help us recover economic value and ultimately gain public trust on some of these technologies. We certainly need policies to accelerate behavior. That is, we can't do this without consumers and the public. And we certainly need to create an ideal future state economic model with costs allocated so that each part of the supply chain is operating sustainability. And that is a big one for me. So for all of this, rather than limiting efforts to just easily recyclable plastics, solutions must account for the full range of materials reaching the end of life. And so achieving this requires long-term science-driven strategies that balance technological advancements with safety, with performance, and market viability. And so this means encouraging innovative technologies such as those that fall into the platform of advanced recycling, while also ensuring that there's rigorous oversight of the potential environmental health and safety impacts. And so all of these plastic management strategies and policies should promote holistic systems thinking and a framework that helps us drive innovation and continuous improvement throughout the life cycle. And so I am so grateful for having you here today, Marco. It has been very enlightening, very educational, and hope to have you back on a future episode.
Rachel, thank you so much for the opportunity. And I think that, the insights and questions that you ask are the ones that everybody needs to have the conversation around and make sure that we drill down to the right answers. So thank you so much again. And I'm looking forward to meeting up again.
Thank you. And thanks for all our listeners for tuning in.
Thank you for tuning in to the Energy Forum. Subscribe and follow our podcast and the Center for Energy Studies for more expert insights on global energy trends. This episode was produced by Maram Hajazi. Until next time, I'm Ken Medlock.